Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, I can answer any questions you may have. Yes. Yes, with very high probability.
Is it a fair comparison with the very normal complexity hardness result there?
So I think the question is, can I clarify this relationship again between the max likelihood algorithms and parameter estimation, and it is. I think the clearest way to see the differences in for instance, the creek problem or the planted bisection, right? That you can define the minimum bisection for any graph, and that's NP-hard. So that's a worst case notion, right? So you can give any graph, and you can define the value of the minimum bisection. And then there's a planted bisection where you have P here and P minus P prime here. Okay, and now with high probability, you can find this bisection. And this is much easier than that.
So the hardness in the first problem.
Yes.
So we give a specific family of instances.
That's right. It is, yeah.
So if we can fit a probability distribution there, such that these families which throw out hard instances are very small and
Yes.
chance of occurrence.
Yes.
Then there are also there might be instances where the algorithm will not
That's
finish
right.
in polynomial
That's right.
time, but we can say that such instances happen only with very less.
That's what we're doing here, right? This is a distribution on all graphs where there's a bisection of this size, right? P minus P prime. So this distribution includes all graphs. It gives a non-zero probability to every graph, right? It's only in the expectation or with high probability that it looks like this. But it does give some non-zero probability to every graph. And so indeed, on those instances, you don't run so well. Yeah? Okay. You have a question?
The parameters of this distribution are P and P prime.
Yes.
The algorithm learned that.
And the set S.
And the so that's not
You can think of it as a parameter, yeah. I mean, it's whatever. It's some hidden... something used to generate it, right? Yeah. Let's say you pick an S, and then you come up with this distribution.
So if we have 1D data, then how do we figure out k-means?
One-dimensional. I didn't. Ravi, you know off the top of your head? I can do it. Algorithm for k-means for one-dimensional data.
I think it's got to be intervals, right?
Yeah.
It's got to be intervals because everybody closer to somebody. So you just take all the midpoints of every pair of points.
It's probably some dynamic programming, right?
It's just a dynamic programming. You should be able to have k-chops and you just take that.
Yeah. Right. So if it's dynamic programming, let's try dynamic programming. I mean, that's what I had in mind. So now the only thing, so in the way I look at dynamic programming is that you're doing divide and conquer. But in divide and conquer, you just divide your instance into two and then forget, you solve this like when you do quick sort or something, right? Or merge sort, I guess. You divide your set into two and then you sort this independently of that, right? So that's divide and conquer. So In dynamic programming, you divide into two, but then you solve the right, keeping in mind the left. Now, to solve the instance on the right, the only thing you need to know is the location of the nearest median over here, or the nearest mean, whatever, right? The center. That's the only thing you need, because everybody will just map to that, right? If they want to map somewhere outside. They won't map to somebody further away, right? Your objective is minimize the sum of square distance to closest center. Square, right? So if that's your objective, any point on this side of the line, right? If it wants to match to anybody over here, it'll be the nearest center. So to solve this, you just need to know the distance, the identity of this center.
Maybe all you need is for every interval of points.
Yes.
What's the best 1 plus string, 2 plus string of the cable, right?
Yeah, that's what I'm doing by dynamic programming.
You don't go across the line. You might as well only take lines where everybody here is trusted and everybody goes separately. I mean, you use K1 centers for this and K2 centers for this. There's no interval. There will be a point. So
There's always a point, you're saying. There's always a point. Ravi is even saying something stronger. That there's always a point where everybody over here matches to centers over here. They never match to centers over there. And that makes sense, yes. There's always a point where the instance partitions cleanly. So in fact, so now you just try all possible places to break the instance. There are n of them. And then for each of those, you solve them recursively, independently.
you solve all intervals in square.
I see, Matthew.
So for every interval, you got to figure out the best K plus string, K max 1 plus string, up to 1 plus string.
Yeah, something like that. Okay, you get the idea, right? We're sort of just thinking aloud, but something like this should work. Yeah. Any other questions?
Just
Yeah.
one clarification. See the transfer cross bisection problem. You said that AC is peak uniform, right? So but actually.
I'm sorry, S is picked. Yeah, any S is fine. Yeah.
Between any distribution of unknown parameters, it's still everything.
Yeah, just S is arbitrary. Yeah, because the rest of the distribution doesn't care about S. Yeah, I mean except for planting the bisection. Yeah.
And you said that if the means are far away, then we can have an algorithm to do this, to figure out the means.
Or the Gaussian.
Yes.
Okay, so you want details.
So can you
Sketch that solution. Okay. So this question is about, the data is equal to points from mixture of uniform mixture of K spherical Gaussians, K identical spherical Gaussians. And the centers are somewhat well separated. So now we want to identify the Gaussians. So this is this uses this observation that I mentioned before that. So suppose you take any n-varied Gaussian, this spherical Gaussian, and you look at any fixed direction, AI, or UI, I guess, U. And I pick a random vector, Z, from the spherical Gaussian. Then the expectation of Z and U, the inner product, is 0. Why? Because this is just expectation of sum over I, zi, ui. And the zi's are Gaussians, univariate Gaussians. So that expectation is 0. And now by the same token, the expectation of the actually, I'll say something even stronger. So this thing itself actually looks very much like a univariate Gaussian. So this projection, z, u, z in a product u. This itself behaves like a univariate Gaussian. Let's see. Why is that?
It's a linear combination of Gaussians.
Right. This is a standard fact. What's the proof? That the projection is itself a Gaussian. What's the easiest way to say it? Yeah. So right. So the Gaussian, the invariant Gaussian is invariant under change of coordinates. But that's the same fact. Okay. Just observe that after you've done a lot of these linear algebra things, sometimes you forget what the axiom is and what the conclusion is. So I'm saying something, but that seems to be equivalent to this, that the Gaussian is sort of spherically symmetric, right? So any direction is the same as any other. But that's sort of the same. Okay. You can prove this, yeah?
E to the minus length of x minus mu squared, right?
Yes.
And you could write the length squared as the sum of the
Good.
x's linear.
Good.
That's
That's it. Good. Right. That's the explanation, right? That the density function is exponential of minus sum of xi square by sigma square. And this expression, the Euclidean norm square, is invariant, regardless of which coordinate direction you take. That's the explanation. Good. So therefore, this actually is itself a Gaussian. Okay. So now. Okay, good. So now, let me just do it intuitively, and you can make this all precise. That suppose these are two centers, C1 and C2. You pick a point from here. Actually, first pick 2 points here. So if you pick 2 points, Z1 and Z2 here, after you've picked Z2, Z1 is pretty likely to be, Z1 is going to be in the expectation orthogonal to this. And it'll have a very low projection over here. So these two are going to be pretty much orthogonal. Okay? And so this distance is basically square root 2 times the radius. Right? The distance between points from the same Gaussian. And it's going to be very tightly clustered around here because this inner product is itself a Gaussian. And Gaussian has a very sharp tail. So this inner product has a very sharp tail. So basically it's close to its expectation up to some standard deviation. And so this is basically very tightly concentrated around square root 2 times the radius, this distance. Now if we pick one point over here, Z3, from this Gaussian, well, we know that this thing will be perpendicular to this, and then this will be perpendicular to this. So by using Pythagoras' theorem twice, the distance from here will be this square plus this square plus this square. Right? So it's square root 2 times the radius. The square root of 2 times radius square plus whatever the separation is. So whatever the separation between the centers. Okay? Do you see the logic again? So there's some two centers. If I pick a point over here, that's going to be orthogonal to this. If I pick a point in this Gaussian, that's going to be orthogonal to this and this. So by using Pythagoras theorem twice, this distance square, or this distance is the square root of 2 times the radius square plus the separation square. Okay? So therefore, if the separation is somewhat reasonable, this distance will be more than this distance. So now if you want to cluster this point, you look at a point and look at all the points that are closest to it. That'll be about this distance. So those are all points from the same Gaussian. And then points from the other Gaussians will have a slightly more distance to it. So you peel away all the points from this Gaussian by just looking at the closest points, right, to this point. Peel away all those points, and now you iterate. So that's one Gaussian cluster, then there'll be another one, and so on.
And what is
That's
the
it.
radius here?
Oh, radius is n times sigma square. Radius is equal to the expectation of sum of xi square. Radius square is the expectation of this, which is n times sigma square.
Why is it
The expectation of this is just linearity of expectation, right? The sigma is the variance in any coordinate, and now I'm just taking the sum of squares over all the coordinates, so just n times the linearity of expectations, right? Okay, so this being a sum of n Gaussians is very tightly clustered around its expectation. So, it's going to be basically the radius, plus minus a little bit. So that's why this distance is square root 2 times the radius, plus minus a bit, and this is square root 2 radius square plus separation square.
and how do we argue that this is one expectation, right?
No, this is all with high probability. So because, this distance is the sum, like this is from here to here, is the sum of squares of IID Gaussians, right? The univariate Gaussians. That's very tightly clustered. So by tightly clustered, I mean that, this can be shown that, the sum of, in fact, sum of IID random variables, which are under some fairly general conditions, sum of IID random variables converges to the expectation.
Okay. And what about that orthogonal thing? So why that?
Same thing. The orthogonal is just remember the orthogonal thing is just the angle between them, which is given by the inner product, and the inner product is itself a Gaussian. So that's also tightly clustered. So it requires a calculation, but that's it.
So as long as the separation is significantly more than the error in inner product,
That's right. So yeah, all of these are just expectation calculations. So you have to calculate the variance, and then the random variable is within its variance, mean plus minus variance with high probability because of the clustering, and then so these calculations are just expectation, but you have to add the jiggle for the variance. Okay, but in the expectation, you can see that within the same Gaussian, the distance is less than between two Gaussians. Yeah, so it's just a very simple greedy algorithm. From every point, take any point, pick all the closest points to it. Those will be points with high probability. Those will be points from the Gaussian that this point was picked from. Remove all those points and continue. So the greedy algorithm that Ravi talked about. Any other questions? Maybe I should mention this Chernoff bound anyway a little bit more, because this we use probably in some of the other lectures, or maybe the other people will use it. That if you have Chernoff bounds, these are called Chernoff bounds. It's just a name that we give to it in theoretical computer science. In other fields, these might be called something else. That if you have, let's say, n identical random variables, say in some, let's say in 0, 1, okay? These are bounded, but there's a generalization, but let's say if they're in 0, 1, then sum of xi is approximately behaves like, this is only an exact statement, approximately behaves like the normal random variable of mean expectation of sum of xi, and then variance, which is expectation of sum of xi. Oh, I see. Yeah, sum of x. Let me just say variance of sum of the variance of xi. Okay. To a first approximation, this is good enough. That for identical random, so they don't have to be identical actually, independent. And independent random variables in 0, 1, the sum of the xi's behaves roughly like, this is a new random variable, the sum of the xi's. It's clustered, it's very tightly clustered, given by the normal distribution, that it's clustered around its expectation, and the variance is the sum of the variances. Okay. So for rough calculations, this is good enough. This is not exactly correct, but it's good enough for rough calculations.
And this could have any distribution and everything else.
There could be any distribution in there, yeah. There are more general conditions where you don't even need them to be bounded, but the fourth moment is bounded or something like that. Ravi has a lot of such theorems too, some extensions. So this is very useful in a lot of settings. So if anybody says Chernoff bounds, this is what they mean. Any other questions? Yes. Excuse me? About Chernoff bounds and VC dimension? Okay, so so let me first say what's going on in VC dimension theory. So think about any model, right? Like mixture of Gaussians or something, right? So you have a mixture of suppose you have some let me try to think of a simplest example. Okay. So let's even step back a little bit, right? So, like we often have these intuitions, right? That let's say there's an unknown rectangle in the plane, okay? Or even simpler, there's a line on the plane, okay? There's a plane. In the plane, there's an unknown line, right? How many points do you need to know on the line before you know the line? 2, right? So now suppose there's a plane in 3 dimensions, right? You need 3 points on the plane, right? 3 non-collinear points, right? So that's some kind of that's sort of the linear algebra dimension, right? The affine dimension. So VC dimension is an analog of that for how many samples do you need from a distribution before you can nail it down, okay? Approximately up to epsilon. So, so it's a measure of that, okay? So it's a measure of the sample complexity. Now, it's not an exact measure kind of like rank. it only gives an upper bound on the sample complexity. Okay? And in all the settings, so there's a more complicated definition in terms of, there's a more complicated definition which I don't want to go into because it's a more general definition which is useful in all kinds of settings, but in the kinds of settings we'll be interested in, we are only interested in these, roughly the linear algebra dimension. So for instance, if there's a random, so if you, let's say there's a box, and inside, so this is say the square 0, 1, 0, 1, and there's an unknown box in here, okay, so axis aligned. And now somebody gives you points from this box. And the question is, how many points do you need before you can identify this box? Okay? And now, those kinds of questions, right? So for each point you're given, is it in the box or not? That kind of thing. So those kinds of questions are answered. And there, the answer, the VC dimension roughly corresponds with linear algebra dimension. Okay, the number of parameters or number of independent parameters that you have. So for us, that's all that's needed. Yeah.
When you made this definition, would VC dimension be able to answer the question that how many number of point classes do we need before we come up with a good binomial approximation?
No. That's not VC dimension. Do you see that as a VC dimension? That's just a simple, yeah, that's just a, I don't think of that as VC dimension.
It's not about how many sample points do we need for a good confidence or distribution.
Yeah.
So, is VC dimension about how many sample points do we need to get a good confidence or distribution?
Something like that. It's not, that's not the technical definition. The technical definition is kind of counterintuitive. But for our lectures, that if you're trying to identify, say, a matrix, the matrix has n square variables, right? It's entries. And so, the dimension is n square. So if you have n square samples which are fairly independent of some kind, you'll maybe find, so things like that. So for us, the VC dimension is kind of like the linear algebra dimension in the kinds of problems we're interested in. Any other questions? So VC dimension is another one of these theories which don't come with an efficient algorithm. So unlike rank, for instance, linear algebra rank. Yeah, VC dimension, we don't know how to compute efficiently. Any other questions?
So yesterday you gave 3 questions, right, for maximum entropy.
Okay.
So the third one, when we had to find for graphs, the
Yes.
images. So then the answer is that all the graphs are equal likely.
Yeah.
So is that just likely saying that when we discrete and discrete points, then the maximum entropy is someone
Is a uniform, yeah.
is
Yeah. In that case, yes. But not for the other ones, right? Like I said, yeah, because those are continuous. Yeah, that's it. Yeah. Yeah, the question was about, the maximum entropy distribution of graphs with m edges. It's just a uniform distribution on graphs with m edges. Because in general, it's a property that if you have a distribution on n points, the maximum entropy distribution on n points is the uniform distribution, where everybody gets 1 over n probability.
in that case, so the mean is fixed, and we have some n points. The bias is not the case.
Why is it not the case? What?
So we fix the mean. So
Mean. Now you're talking about generally max entropy,
yes.
or general max entropy. Okay.
So there, even if we had some endpoints, then the max entropy would be exponential, right?
The max entropy distribution would be
Exponential.
n points. No, so exponential distribution is a single variate. I'm not sure what you mean. It's a univariate distribution. Yeah. Okay. Any other questions? Yeah. Excuse me? This proof, the one I didn't show? Uh-huh. You want to see this proof? Okay, let me sketch it for you. So let u1 through uk be the top k eigenvectors of A. It's eigenvectors, and they are all orthonormal, right? Okay, now, sorry? Okay, so now AK the rows of AK are spanned by U1 through, or let's say columns of, these are column vectors. Columns of AK are spanned by U1 through UK. Why? Can somebody prove that for me? I'm sorry?
Everything in the range of ticket is spent by equal.
Okay,
So follows the
good, okay. Yeah, what I had in mind was just looking at the expression, which is summation sigma I ui transpose I equals 1 to k, right? That's AK. And here again, by examining, by just, it's some vector times, some combination of those vectors. But that's another way to see it. Okay, so columns of AK are spanned by U1 through UK. And so extend to a basis U1 through UP, orthonormal basis, for column span, for column space, column for subspace spanned by columns. Of the columns of A, AK, and columns of B. Okay, B is itself of rank K. So therefore, P is less than or equal to 2K. Because the first K vectors already span the columns of AK, and then the columns of B may at most have a dimension at most K, so at most 2K vectors will span the entire set, the columns of A, K, and B. Okay, now AK minus B, Frobenius norm square, is equal to just add A and subtract A. Usual trick. So is equal to AK minus A plus A minus B Frobenius norm square. I'm just adding and subtracting A. Okay, and now use triangle inequality. This is by triangle inequality. No, wait, is that what I do? Yeah, but not by triangle equality. What's this equality? A plus B square is less than or equal to 2A square plus B square. I don't know what it's called. What's it called? Cauchy-Schwarz. Good, right. That inequality. Yeah. Everybody's seen this inequality, right? For vectors. This is for vectors. Is less than or equal to 2 times A minus AK square plus 2 times A minus B square. No, wait, this is it right now? What am I doing? I have it written somewhere on my notes, and so I'll just look at it.
No, you don't want to go through.
I don't want to do this?
No. I mean, you want to say that A K minus B for A from A K minus B times you want to do P.
Oh, right. That's the way you go. That's right. That's the way. Right. Now, yeah. Of course, I introduce U1 through UP. I'll do this later. Yeah. Thank you. Okay. Right. So this is just taking the L2 square norm of the rows of A, of this matrix. I'm sorry. So that's just exactly equal. And since the span of these is U1 through UP, that's exactly equal to summation of AK minus B times UI squared. That's what you do next. Right. Now I'll do. Okay, so this you do. Right? So this is just because this is the sum of the norm square of, I'm using something else. So if you're trying to do the sum of the norm squares of some this is hiding something. So if you have a vector, right? If you're taking its norm square, length square, it's just exactly equal to the sum. So this is a vector x. It's just the sum of x times ui square, where ui is an orthonormal basis. Okay, and And so we're taking this, the length square of all the columns of this, right? That's the Frobenius norm. Remember, Frobenius norm is just the sum of the length square of mi square, right? Sorry, the square doesn't have a square root. Right? And so therefore, and now this length square is just the sum of the projections on the UIs. Okay, so that's why you get this. Now you break this up into the first k and the remaining. So now break up into summation I equals 1 to k, ak minus b ui square plus summation I equals k plus 1 to p ak minus b ui square. Okay, so I'll continue up here. But now, what's AK times UI? That's actually equal to A times UI for I less than or equal to K. Right? Because this is just taking the first K, right? The first K eigenvectors. So AK times UI is just sigma I times UI, right? And that's the same for A or AK. So this is exactly that. So therefore, this term becomes, this is exactly equal to A minus B. What do I want to write it? Less than or equal to, this is K times A minus B times UI, which is, let me first write it. This is equal to, let me write it here, this first term. So this is exactly equal to summation I equals 1 to K of A minus B UI square, right? Okay? But now remember that this is less than or equal to K times the sigma max of A minus B square, right? Because this is, sorry? Right? So this matrix, how much does it blow up, right, when it applies to a unit vector, right? So it's at most sigma max. So this K times, so this is less than or equal to K times A minus B square, right? 2, right? So that's K, right, out of the 5K. So now the remaining 4K has to come from somewhere. That'll come from the remaining ones over here. Okay, so let's do that. So now this one. Right, so here I want to use that inequality that I took out. Yeah. So here I'll write this as summation I equals 1 to P A minus AK A minus A plus AK plus A minus B times UI square, like that. Sorry? I'm sorry?
Is it AK times UI? 0 is the range K plus 1 to P?
Oh, right, sorry. It is, yeah. Right. So that's the first step. So, right, AK times UI equals 0 for I bigger than K. So therefore, this becomes, that's right, indeed. First, it becomes B times UI square, I equals K plus 1 to P, which then becomes summation I equals 1 to K plus 1 to P of A minus B minus A UI square, which is now we use that inequality that I wanted to use long ago. So this is less than equal to 2 times summation I equals K plus 1 to P of A minus B UI square plus 2 times summation I equals K plus 1 to P of A times UI square. Okay. But now, okay, so this again by the same thing, right? So this is less than equal to 2 times K times sigma max of A minus B square, right? So this is contributing another 2K over here. So we got K here, we got 2K here. And now we've got this one left. Now A of UI A times UI is less than equal to sigma K plus 1 of A square. Which is less than equal to A minus B sigma max square. So this requires an explanation. So this inequality, let me just explain it here. So sigma max of A minus B square is at least sigma K plus 1 A square. So we want to prove this.
Can it be equal to AK? That will be max.
That's right. So this is true. So this is true. B is any rank K matrix. Even for the best, so the best rank K matrix would be AK, and even there this would be at least sigma K plus 1. Because B is only of rank K, right? So it cannot eat away more than the first K eigenvalues. So B cannot reduce this below that. Because the most that can be reduced is by eating away the top K eigenvalues out of A. Maybe I haven't said this clearly enough. So A, right, from its expansion, right, we know that it stretches vectors along the first K directions by sigma 1, sigma 2, up to sigma K. Now, B could zero it out, right, what it does to those first K directions. But it cannot do any more because B is only of rank K, right? So therefore, among the first K plus 1 directions for A, right, the largest ones with the largest stretch, B can cancel out K of them, but it'll leave 1. So therefore, it's at least sigma K plus 1. So that gives you the last 2k times sigma max of A minus B. That's this lemma. Any other questions? We're almost done. No other questions? Oh, one more. Okay. Excuse me? For what rank?
Yeah. Is there a way, apart from measuring the eventual performance, is there a way to find the measure?
No.
So it's like you see whether it's performing better than the
Yeah. I mean, you could have matrices which need all k eigenvalues, right? You could have matrices where all the eigenvalues are the same, or roughly the same. So, yeah, in general, matrices don't have low rank approximations. Random matrices don't so much.
So how does this use, so say singular vector decomposition or NSF or that
Excuse me?
so all these approximation techniques like
Yeah.
singular vector decomposition, do we like plan the tool?
I'm sorry, do we what?
Okay, we want the rank of this matrix of this rank as an approximation. Do we give that number K or is it like
Yeah. So for instance, in this case, we were told that the graph came out of the planted bisection problem, so k is 2. Okay, but in general, yeah. Based on the model that you've been told for the matrix, you have something in mind. Right?
If the difference is the input, that how much A minus B norm I can tolerate. So then you can, that the error they get from the rank approximation is the K plus 1 eigenvalue. So
Yeah.
So we can figure out.
Yeah, for any particular matrix. I want to mention one cool thing, which I had people implement in my class. So, suppose you have a grayscale image. Okay, by grayscale I mean that actually not grayscale. The 0, 1, not grayscale. What's it called? Binary image. No, I'm talking about images. Images where it's 0, it's either black or white. Bitmapped, yeah, right? Bitmapped image. So it's a bitmapped image, right? So kind of if you look at a newspaper image with a magnifying glass, you'll see that it's bitmapped. It's just there's no gray in there. It's either they achieve the effect of gray by just having fewer black dots, okay, mixed in. So it's a bitmapped image, okay? So it's 0, 1. It doesn't have to be, actually it works for grayscale too, but okay, let's say it's a bitmapped image. And now this is, let's say, I don't know, 1200 by 1200 pixels, right? Let's say. Okay? It's a huge number of bits, right? 1200 squared. So you think of it as a matrix of dimension 1200, okay? So think of it as a matrix. So image is equal to A, right? This matrix. Now for this matrix, you compute this spectral decomposition, and you see when the eigenvalues drop off. So you plot the eigenvalues, and they drop off at some point, and they start getting small. So the first few are significant, and something like 30 or 40, they drop off already. Okay, so that by around 30 or so, the eigenvalues are dropped off. 30, 50, something like that. Okay? And so now you just take the corresponding eigenvectors. Okay? And now there's your approximation to the matrix. And so if it's an approximation to the matrix, it has roughly the same, it's an approximation of the image. So it's just a way of compressing an image. It's a very elementary way of compressing an image. So the question for you is, why does this work? Think about it, So given what you know about images, why should this work? So it always happens, you take 50 or 60 eigenvalues, and now you just truncate, the rank 60 approximation to this matrix. And that actually is a very good, visually looks very similar to the image.
So, roughly, maybe you could say that we've basically taken some regions in the image and filled them with black blobs. So it's like saying we have taken some almost white thing, and we have filled some black leaks at various points. So
That's not clear to me that that's what this is doing, the low rank approximation. Yeah, not clear to me. Is it? Yeah, think about it. It's not. Yeah, so think about what images are like. Yeah, you're sort of on the right track. That images aren't sort of a random matrix, right? There's regions of whites and blacks and so on, and so we know that images are compressible, highly compressible. And this is a very simple way of compressing an image. So yeah, think about it, what images are like and why, and from that come up with a reason why they should work. So this is going back to that, the first level of making up that I was talking about, right? Coming up with a model. So now you're thinking from first principles, what's an image like, and what's a model for what an image is? Right? And from that model, you're going to say somehow, low-rank decomposition should compress the image. Okay, I think I'll stop if there are no other questions.